So to finish up the day, the idea is to go through an exercise on multi-event models. So it's exercise 4. And so the purpose, the aim of the exercise is to build models incorporating uncertainty in the assignment of breeding state. So it's basically the same example as in the lecture. And so we will use data on sooty shearwaters, Puffinus griseus, or TTs for short. And these data are from the 40s and 50s, and they were collected by Lentz, Richdale, and it's Mike Schofield who shared this data with actually when I was doing a PhD, and he kindly shared this data that he reanalyzed in a paper in 2001. And so the data we have 4 states: breeder, so successful breeder, accompanied by another bird, alone in a burrow on the surface because they breed in burrows. And when Mike tried to treat a multi-state model, I think he had some issues with when he considered all these states separately. So he just pulled together state 2, 3, and 4 together in what he called a non-breeder state. Okay, so at the end of the day, we just have a non-breeder state and a breeder state and a dead state. Okay, and I took this data, and what I did is that I artificially generated some uncertainty in the assignment of the 2 states, successful breeders and or breeder and non-breeders. Okay, non-successful. Well, non-breeder is the pooling of 2, 3, and 4. And by doing that, I think it's helpful. Well, it's a fake data set at the end of the day, but it's helpful to understand how uncertainty is generated, where it comes, where does it come from, the uncertainty, where it comes from. Sorry. So for each individual, at each detection occasion, what I did is I said, okay, for a successful breeder, for a breeder individual, we will assess it as a successful breeder with some probability, say 20%. Okay. And when it's assigned to the breeder state, we will say, okay, the breeder state is 1. It's observed in the observation 1, right? And if it's not assessed, we cannot say it's that it's a successful breeder. We're going to say, okay, it goes in observation 3. You remember in the lecture example, with a probability 0.8, okay, the complementary probability. Now, for the non-successful breeders, we would say, okay, we assign them to the non-successful breeder state with probability 0.7. Why not? And then go in observation 2. And if we cannot assess their state with probability 0.3, we assign them to observation 3, okay? Like for the successful breeders, for which we cannot assess the state, okay? So we generate uncertainty in the assignment of the breeding states, non-breeder or successful or breeder. Okay, and you have the code to do that. Well, it's just for you to see how I did it. The script make uncertain.r, where I just go through the multi-state data, the multi-state data set, and for each individual and at each occasion, I decide whether I assign the state or not using these probabilities here. So basically, I create a new observation 3, which corresponds to an individual that is detected. Okay, so we know that it's alive, but we cannot say whether it's a non-breeder or breeder individual. So it's really, really, really similar to it's the same example as in the lecture. Okay, so these data are in this text file here. Okay, I'm gonna do something. I keep getting those error messages, warning messages. Okay. So I read in the data, and so we have threes, which correspond to detected, but we cannot assign a state to that individual. The dimension, so we have 1,000 individuals and 7 capture occasions. Okay, and we're gonna fit a model, a multi-event model, with constant parameters. Okay, so we're gonna have the two states, the two breeding states, and the transition between those states. But we're going to account for uncertainty in the assignment of the state to an individual. So it's a multi-event model fitted in Jags. Okay. So I'm gonna go through it with you, I think, because it's well, it's kind of a well, you can, I don't know. Let me double check. Yeah, you can try yourself. Try it yourself. You can go through the code. I mean, you don't have to. I mean, I'm not asking you to write the model from scratch. So go through the code and make sure that you understand every step. Michael, I think you answered the Heiko questions to me only.
Ah, okay, sorry.
No, that's fine. It's just for Heiko. It's not very, yeah. It's not a paper that I shared in the chat. It's the picture of Frédéric Gosselin with the slides of his, which says Winbugs freezes the modeler in you. So it's in the Dropbox. It's a picture. Well, the context is that we have a working group where we're working on hierarchical models. And I think the point that it was 4 years ago. So as far as I remember, the point that Frédéric was trying to make is that the bugs software is awesome. The software are awesome because you can do all the models you want. But the risk is that you end up doing very complex models that you're not sure are, for example, totally identifiable, or you get issues in a state space model that you don't even you're not even aware of because you fitted these very complex models. That's related to a paper I mentioned yesterday by Marie Rogemete on the something about the devil is in the details of state space models, and yeah, something that Michael mentioned also about observation error and the fact that when it's larger than the state process error, you get into trouble. Okay. Any questions, or it's the end of the day? Huh? It's difficult to go through that example at the end of the day. It's probably the most complex model you can do with capture-recapture data. In the list of pointers only. Why is this? You mean here?
Hi, sorry, I've just unmuted. Can you hear me?
Yeah.
In the kind of thanks. In the list of parameters above, so not when you actually set them, but in the commented list above, it's only PI for the non-breeder. So I was just wondering if that's a. Oh, okay, I thought it might be, but just wanted to check in case I've missed something.
It's a typo.
Okay, thanks. Thank you.
You're welcome. One thing we haven't seen together is, you know, when I decompose the observation matrix in 2 steps, what I mean by that is it's a product of 2 matrices, the encounter matrix and the assignment, the assessment matrix. And in Jags, it's not the case in Windows, but in Jags you have the matrix product. So this is what I do here. I actually decompose my matrices in 2 steps. Same thing for the transition matrix. I use a matrix for survival and then another matrix for the movements. And then I say, okay, now the transition matrix is just the matrix product of my survival matrix and my transition matrix, my movement matrix, sorry. And the matrix product is given by that in R and in Jags. Okay. So it's nice to see it in terms of calculations in R and in the MCMC machinery. It's not really very clever to do that because you have the matrix product, which is kind of it's demanding in terms of time computation. So it might be better to directly write the whole matrix together, the transition matrix together with survival and and the survival parameters and the transition parameters in the same matrix. Not to do the matrix product here. It slows down the computation for sure. But I thought it was nice to show you that you can do that in R. You can have in Jags. You can have the matrix product. Okay, so it's really the only thing that differs from before. The likelihood is really the same as in the multi-state models. Huh? You have the Z that are taken in a categorical distribution, and the observation that are taken in a categorical distribution as well. Okay, it's just that now we have to have this Z here. It's no longer a deterministic link, but we have to take it in a categorical distribution as well. Okay. But then the way you build the transition and the observation matrix is really matrices is similar to what we were doing with the multi-state models, right? So it's a simple model. Oh, it's a simple. No, it's not simple. It's a model with constant parameters. And you see that the observation and transition matrix are just, they don't have the individual and time dimensions. Like I said, it's just to make the whole fitting process a bit faster. But if you were to consider, I don't know, individual covariates or time covariates on the survival parameters, you would have to plug back in the individual or the time dimensions in those matrices here. Okay.
Olivier?
Yeah.
Yeah, can I just ask a question considering the initial states? Because I don't really understand. In the previous multi-state model, you didn't, or maybe I missed something, but you didn't define any initial states in the classic multi-state model. But in this exercise, why do you define initial states in addition to the observation matrix and transition matrix?
You mean here?
Yes.
Oh, oops, sorry. Here. Well, in the multi-state model, you have those probabilities here. The probability of being in site A or site B at initial state. It's just the proportion of individuals that you first capture in site A or site B. Those parameters are actually in the model, but we never estimate them, but because it's just the proportions, we have them already. Okay. Whereas in the multi-event model, you have to estimate this proportion here. You don't know it. You don't know it before you feed the data you feed the model to the data.
Because there is the uncertainty.
You see because there is uncertainty, exactly. Okay. Okay. Whereas in the multi-state, I mean, you could apply this model on the multi-state data we had before, and you would estimate this the proportion of individuals at first encounter that were in site A, and you can calculate exactly the same thing, the proportion, the observed proportion in your data. You just count how many individuals were in site A at first encounter, and you would get exactly the same value as the one that you estimate from your multi-event model. So you don't need to estimate it; it's already in there.
Okay, so I got it. Thanks.
Yeah. That's a good point. That's a good question. Okay. There's a question in the chat. Yeah. And in passing, this code here, it's the code to fit any hidden Markov models in Jags, not necessarily on capture-recapture data. So it's the kind of code you would need to, I don't know, to fit the example that Michael showed at the very beginning of his lecture about tracking individuals with GPS data, for example, and hidden Markov models are often used to try and decipher the fate of individuals, the trajectory of individuals, and we use hidden Markov models to do that, where the states are the location and the observations are just the data we get from the GPS tools. Oh, okay, it's done. We can have a look at the trace plot, but the panel is too small, so I need to do it again. Here we go. So we get an estimate for parameters that are very similar to multi-state models: survival in each state, transition probabilities between non-breeder and breeder states, or the other way around between. Oh, in that case, what I did, yeah, something you might have noticed. What I did is, yeah, the way I parameterize my transition matrix is a bit different from what we've seen so far. I just said, okay, I want the probability of staying in state breeder and the probability of going from state non-breeder to breeder. It's a way to assess reproduction trade-offs. Okay, if you were a breeder individual in time t, at time t, what's the probability for you to stay as a breeder individual compared to the probability of going from non-breeder state to the breeder state? Is breeding costful in terms of reproduction? And you can compare the two probabilities, or you can fit a model with a, you can compare the two probabilities and assess whether there is a cost of reproduction on the next reproduction. Okay, that's a way to get an answer to this question. And I scroll, yeah, that's okay. And then I get an estimate for the delta parameters, the probability of assigning an individual, correctly assigning an individual in each state, on breeder and breeder. Okay, and the estimation, the parameter estimates. Okay. So the delta parameters, I think we used 0.2, yeah, for the delta B, and we used 0.8 to generate uncertainty for the non-breeder individual. So it's not that bad. Huh? We managed to recover the kind of the true value that we used to simulate uncertainty on top of the real data, the real soot tissue water data. And yeah, okay, so you see that the effective sample size is quite low, and yeah, that was to be expected. I mean, I just run 1,000 iterations, so if I wanted to really do inference, make inference from these estimates, I would need to run that for a bit longer to get higher effective sample sizes. Okay, well, I'm done for today. Do you have any questions or comments? Is there anything you'd like to discuss? I don't know. Or you're just